Hello everyone, and welcome to our first video for AP Calculus for this school year. This first video is called a preview of calculus, and really the idea behind this section and the first one that we work with is to really draw the connection between what we did last year in pre-calculus and what we're going to do this year in AP Calc. So let's get started. Here are lesson objectives for this particular video. Number one, we want to understand what calculus is and how it compares to pre-calculus. Number two, understand how the tangent line problem relates to calculus. And the third thing is understand how the area problem relates to calculus. The first thing we want to do right now is really talk about what is calculus. And the thing you have to remember in this, calculus is the mathematics of change. In calculus, we work with to find velocities, accelerations, tangent lines, slopes, areas, volumes, arc lengths. There's things like centroids, a lot of different things we find. And you might be looking at this saying, wait a second. We dealt with velocities, accelerations, tangent lines last year, slopes last year in pre-calculus, and you dealt with some of these in previous math classes as well. So what's the difference? The difference is that in the stuff that you worked with in pre-calculus and before, things were much more static. They were much more set in stone. You looked at, in terms of finding a slope, you needed 2 points. You need to know 2 points to find the slope of a line. We also, when we talk about slope in pre-calc and in other math classes was typically something you talked about with a line. Well, when we get into calculus, slope now also is something we can talk about with relation to a curve that we see. Also, when we talk about areas when you dealt with in previous math classes, areas were for figures that we knew a formula for. And they were kind of very solid set formulas. Things like the area of a circle, the area of a rectangle, a square, a parallelogram, trapezoid, those types of things. And as long as we could work with those types of figures, we were able to go and come up with the area. But if we had a area of a region that was bound by curves, we would not be able to find that area. Where in calculus, we can find that area. You might recall last year when we dealt with limits. At the end of the year, we dealt with some limits, and we actually used limits to go, and we introduced one of the concepts that we're going to be spending a lot of time with in calculus, the derivative. Well, that limit process that we have, that is really the key that takes us from pre-calculus to calculus. So when you do this, you have this thing called the limit process. So it's going to take pre-calc. We're going to have this limit process. And that's what's going to take us into calculus. Calculus looks at things where in pre-calculus we were always finding the average velocity. In essence, every time you found a velocity or an acceleration, it was an average velocity or average acceleration. When you found a slope, you were always finding the slope of a line. When you found an area, it was always a nice geometric figure. Volumes were the same thing, nice geometric figures. Arc lengths, we talked about arc lengths with respect to circles. What happens in calculus? We don't talk about average velocity so much. We talk about the instantaneous velocity. How is something changing at that particular instant? Okay, when we look at areas, we're looking at the area between two curves. We're not going to be defined. We're not going to be stuck just working with basic geometric figures. We're going to be able to find volumes of wide variety of solids. And same with arc lengths. Arc lengths, we will find the length of a curve. You can actually use calculus to find the length of a curve, of any curve that you have. So one of the things I'd like you to do right now, I want you to pause the video and open up your book to page 43 and 44. And take a look. What you see on the left-hand side of each one of those pages is going to be what we do when you have without calculus. And the right hand of the chart, right-hand side of the chart is going to tell us what you can do when you have calculus. So pause the video, take a look at those right now, and identify some of the things that you'll be able to find. Welcome back. I hope that you got to see some pretty interesting things and you're kind of excited about what we have coming up for us. Please remember on this that we're not necessarily going to be working with doing every single one of those here. For example, when you talk about, there's the one dealing with the tangent plane to a surface. That really is when you get into what's called multivariable calculus, or what is called calculus 3. But a lot of the other things we will work with as we progress through these. Now what we're going to do is we're going to go back in time a little bit. We're going to go back to what we were doing at the end of last year. And we're going to look at the tangent line problem. Now here we have a diagram that I've made on here as best I could. And what we have here is we have our curve, y equals f of x, and that curve is right here in black. And we have 2 points. We're going to put some number in, we're going to call it x, and put it into the function and into y. And we're going to get this point here, whose coordinates will be x and f of x. Then we're going to move over from x, we're going to move over a set distance, some distance. And that distance has the symbol we use here is going to be this triangle, which is read as delta, and that's called delta x. And what delta x means is that means that you're dealing with the change in x. So when I go from x, move over delta x units, I will be at the x coordinate of x plus delta x. And when I plug that value, that x value, into this function, I get x plus delta x, comma, f of x plus delta x. So the point here is f of x, and the point here is x plus delta x, comma, f of x plus delta x. Now this is going to look a little bit familiar to you because last year instead of delta x we used h. Okay, so if you want to replace the delta x's with h, you can go ahead and do that. Our book works with the x plus delta x, so I will primarily use x plus delta x in terms of the problems that we have here. But if you want to replace those with h, that would be fine. And what happens here is we're going to go through and we're going to use these 2 points to find the slope of the line. Slope of the line is change in y over change in x. And so when I do that, my slope, m in this case, is going to equal the change in y, f of x plus delta x, minus f of x, all over x plus delta x, minus x. And when I combine the like terms, I get f of x plus delta x minus f of x all over delta x. And we go through on this, and we can then go and use that that will give us a slope. And then what we do on this is as we make delta x smaller, let delta x get smaller and smaller, our point here is going to move closer and closer to what we started with. And as that point gets closer and closer and closer to where we started, we're going to get a better estimate for the curve, for the slope of the curve at x. So we're able to go and give our estimate of that slope by using this idea right here. And that is called the difference quotient. You probably remember that from last year. We dealt with it at the beginning of the year and at the end of the year. When we go through and apply the limit process to this, you might remember what term we called that. That was called the derivative. Let's take a look at an example problem now. What we're going to do here is we're going to use a real basic example. We're going to y equals x squared, and we want to explore the tangent line at the point 1, 1. And so what's going to happen here? Instead of going through and doing things symbolically, we're going to actually use numbers here. So we know we have, in this case, we're dealing with, we want to find working with the tangent line 2x squared at this point 1, 1. So we know that's one of our points. And what we do on this is we can go and find some of this stuff by going and picking values of x that are close to x equals 1. So the first one we're going to use is x equal 1.5. And when I put 1.5 in for x, I will get y equals 2.25. Another point, each time as we do this, we're going to go through and get closer and closer. So the next one we'll use x equals 1.1, much closer to 1 than 1.5. And when I plug that in, 1.1 squared, y is going to equal 1.21. And we can keep going closer. And each time, so the next one, I'll go x equals 1.01. And then, when I put that in for x, I will get y equal to 1.0201. And so here's 3 points. And each time as we go in this down here, you're seeing that these values here are getting closer and closer to 1. And we have function values here that we're going to use. So I can go and approximate lines. In this case, this will be my first one. Here's number 2, and here's number 3. So for number 1, when x is 1.5, y is 2.25, we'll use, our slope we'll use is going to be m1. And we can look at that. We can go and just take the slope between the 1.5, 2.25, and 1, 1. And so I'm going to get 2.25 minus 1 over 1.5 minus 1, which will give me 1.25 over 0.5. And what I have to do now on that, I can go and do the division. And when I do that, that comes out to be 2.5. I can go and do a second slope, m2. m2 is going to be the slope between the point 1.1, 1.21 and the point 1.1. So when I do m2, I'm going to take 1.21, change in y, 1.21 minus 1, over 1.1 minus 1, which when I do that, that will give me 0.21 over 0.1. And when I do that division, I'm going to get 2.1. I can also do a third slope using my the third point that I have here when x is 1.01 and y is 1.0201. And so I will go and plug that in, find the slope, change in y over change in x. So I'll get 1.0201 minus 1 over 1.01, which when I do that, that will give me 0.0201 over 0.01. And when I do that calculations, I will get 2.01. And so what you can see on this is that as my x values here, as these x values are getting closer and closer to the x coordinate of my point of tangency, my slopes are also approaching a specific value. And that specific value in this case appears to be 2. So we would look at this and we would say, based on what we see here, that we might say that the slope of the tangent line is 2. What we can do is we can kind of confirm that by going through and finding a fourth one. So what I want you to do is we're going to go and let x equal 1.001. So even closer to 1. So what I'd like you to do is pause the video and then find the slope of the line that would connect the point we have here when x is 1.001 and the 0.11, and see if that kind of matches up and confirms or contradicts our idea, our assumption, that the slope of the curve at x equals 1 is actually 2. So pause the video. Once you're done, come on back, see how you did. Welcome back. Now in this case, I asked you to go through and find the slope of a line when that would connect the point when x is 1.001 and the point 11. Well, when we put 1.001 into x squared, we will get our y-coordinate is going to be 1.002001. And so the slope we have here is just going to be 1.002001 minus 1 over 1.001 minus 1, which will give us this. And when we go through and actually do that calculation, that will come out to be 2.001. And so we can see that even moving closer, we still are continuing to get closer and closer to 2. So in this case, I would say that I have enough information to be reasonably certain that my slope of my tangent line of x squared at the point 11 is going to be 2. Now let's take a look at the area problem. Now the area problem, what we're trying to do here is we have our curve right here, y equals f of x. Y equals f of x. And we have these two x values, x equals a and x equals b right here. And those values there combine with the x-axis and our curve to go through and give us a region here, this region right here. And what we want to do is we want to go and figure out what that area is. And to do that, we will go through and use some basic geometric figures to help us out with this. We will use rectangles. And we get these rectangles by doing what's called a partition. A partition of an interval just really goes and breaks the interval up into pieces. So in this case, I'm going to break my interval up into 4 pieces. So I'm going to do that by drawing in some vertical lines. I'll draw one here, another one here, and there. Now the thing to remember on this, when we deal with a partition, the partition itself does not have to have you don't have to break it up into the interval up into equal pieces. If the pieces are equal, that will be called a regular partition. But for our purposes right now, we're not concerned about getting a regular partition. We just want to break this up into pieces. And what happens then with this is we can then go and use different points here to go and come up with areas of we'll come up with a rectangle, and then we can use that rectangle to approximate the region. Now one of the things that you'll find will be a rectangle like this first one, where the base of the rectangle is entirely below the curve. That is going to be, in that situation, we have this rectangle would give us an underestimate of the area in that region, but it is an estimate, so we'll go with that. And then another one we can do is we can go, again, we'll do another lower one. We can just connect it right there. We have our second rectangle would be an underestimate. We can also go from the other side or at a higher point and go here. So in that case, in that third rectangle, that would be an overestimate. And again, it's okay. You can have that. And the other thing you can do, you don't have to go at the endpoints. We could go somewhere between there and create the rectangle that way. A lot of different ways to go and create your rectangle. But the point that you have on here is that in each one of these rectangles there is a height. And the height of that rectangle is actually found by finding a point, the y-coordinate of points on this curve. For example, in the first rectangle, the height is going to be the y-coordinate of this point right there. In the second rectangle, it's going to be the y-coordinate of this point. The third rectangle, the height is the y-coordinate of this one. And then the fourth one, the height is actually the y-coordinate of this particular point, where the top of the rectangle touches that curve. Okay. The other thing you have is that there is a base. The base of the rectangle is really it's really just a change in x. So in this case, if I go to that second rectangle, my base is there. And we could, again, use that as delta x. And in this case, because it is the base of the second rectangle and we don't have a regular partition, we'll call that delta x sub 2. So this one here in the first rectangle would be delta x sub 1, and then delta x sub 3, and then delta x sub 4. Now, once we know what our base is and we know the height, we can approximate the area in each one of these subintervals of our partition. And we calculate that by just finding the area of that rectangle. So we'd find the area of this rectangle, the area of this one, and that one. And we could then go and add those up, add those areas, and that would give us a better approximation. Or it would give us an approximation of that area. Now, we could get a better approximation by increasing the number of rectangles. If we go through, the more rectangles we have, the better approximation I'm going to get. But that's going to require that all my delta x's kind of get smaller as I do this. The more rectangles I have, the better approximation I'm going to get. Now, for our purposes, these two examples, the tangent line problem and the area problem, really illustrate the two basic branches of calculus. You have one of them which is called differential calculus, which deals with the derivative, and the other is called integral calculus, which deals with this particular problem we're talking about here, which is often called, when you're finding the area of that region, it's called let me get the pen, it's called the definite integral. So those really, the integral calculus is going to be something we're going to deal with a little bit more later. We're going to start out, most of our focus initially is going to be with differential calculus, but this gives you an idea of what is going to be happening throughout this year. So with that, we have now concluded our first video for AP Calculus for this school year. So with that, I hope you're feeling well and you're ready to go, because on the next class, we're going to start doing some problems. So have a good night, and we'll see you in class.